Okay. Hi everyone. My name is Somayeh. I am from University of Tabriz. I'm going to briefly talk about MHD wave behavior in the vicinity of a magnetic null point. Different observation studies have shown the presence of numerous magnetic null points in solar atmosphere, although other observational works have illustrated the MHD waves in the solar corona. Then, MHD waves, through their propagation, inevitably interact with null points, and this interaction could provide insight on events such as magnetic reconnection, coronal heating, and solar wind. Therefore, it's worth studying the behavior of MHD waves around the null points. In this line, an initially symmetric Alfvén pulse at a specific distance from the null point is kicked towards it. Here we have an X point with this background magnetic field structure. Important properties of an X point are magnetic null point and separations. Magnetic null point is located at the origin and magnetic field is 0 there, and separations are located along X and Y axis, which separate four areas with different connectivity. Here we have the behavior of Alfvén wave around the null point. Due to the nonlinear effect, Alfvén wave has lost its initial circular shape and accumulates along the separations. It must be noted that one of the important characteristics of fast magnetoacoustic waves is their refraction around the null point. Since there isn't any refraction around the null point, then it could be concluded that in nonlinear regime there isn't any coupling between Alfvén wave and fast wave. Propagation of Alfvén wave around the null point results in fast wave perturbations, and here we have the behavior of fast wave around the null point. As we see, fast magnetoacoustic wave also moves toward the null point and diffracts around the null point. And due to the non-zero plasma beta approximation, we also have a slow magnetoacoustic wave perturbation. And again, because of the refraction effect, a slow wave focuses toward the null point. As we said, we introduced an X point to the system and found that magnetic field structure is constant over time. Then Alfvén wave propagation toward the null point doesn't lead to the magnetic reconnection. And here we have X component of the plasma flow, and the blue colors indicate negative values of the velocity, which proves the presence of inflows, while the red colors indicate positive values of the velocity and outflows. And it could be noticed that the flows induced in Y direction have a broader range compared with X direction one. And in the second simulation setup, an initially symmetric fast magnetoacoustic wave is introduced to the system. It must be noted that every parameter is similar to the first setup with initial Alfvén wave, so it could lead us to investigate differences between Alfvén wave propagation around the null point and fast wave propagation around the null point. As we see in our initial pulse, naturally is divided into two waves, which called incoming and outgoing waves. Outgoing wave propagates toward the boundaries, and it's not our aim of study. Incoming wave moves toward the null point and refracts around the null point, and refraction of the fast wave around the null point leads to the current density accumulation at null point that we discussed later. Here we have refraction of the fast wave around the null point. Here we have a slow magnetoacoustic wave behavior. At first, we have very slow wave because actually we introduced an initial fast wave, and a slow wave moves toward the null point and refracts around it, and because of the non-zero sound speed, waves go through the null point, and spreads around the magnetic field lines. And the important point is that it's interesting that a slow wave has a significant amplitude, And since slow mode has a dominantly acoustic property, then amplification of the slow wave could result in plasma heating. That's interesting. And here we have currency profile. Currency is zero. Currency is zero at first because our equilibrium structure is curve-free due to the diffraction of the fast and slow wave here. Currency degenerates at null point, and because of the spreading of the slow wave around the magnetic field lines, we have a currency accumulation around the field lines, and it's interesting that through high currency accumulations that tearing mode gets important, block structures are excited. And here we have magnetic field structure through the propagation of fast wave around the null point. Magnetic reconnection starts happening during high current density accumulation. After some frequent magnetic connections, initial magnetic islands or O point appear. At first, magnetic islands or plasmoids limited in a small area, and they surrounded by 2 X points. Then after each plasmoid mediated magnetic reconnections at X points, the size of the magnetic islands gets larger and larger. So it's found that fast wave interaction with the null point leads to the plasmoid generations in solar coronal condition. And here we have counterplot of X component of the magnetic field, and it illustrates sensible twisting of the magnetic field. So it's expected that tension force could lead to the significant plasma flows. And then here we have plasma flows profiles. In a matter of fact, through the null point reconnection, plasma flows toward and outwards of the reconnection side are described as inflows and outflows. Note that the red color indicates positive values of the velocity, that refers to outflows, and the blue color corresponds to negative values of the velocity and inflows. And the important point is that flows during the plasmoids cover larger area and also have stronger amplitude. We could conclude that plasmoids in coronal condition could contribute to eruptions. We also have a Y component of the plasma flows, and again we have somehow a similar behavior. And now I want to highlight the energy transfer via the interaction of fast wave with null point. We have magnetic energy, kinetic and acoustic energy. At first glance, we see an equivalation of kinetic and magnetic energy that is expected because of the magnetic connection. Since fast mode has dominant magnetic character while the slow wave has mostly an acoustic property, then with considering these two figures, it's clear that mode conversion happens here in this layer. Whenever the sound and alpha and space are equal, we have mode conversion. Apart from this layer, fast and slow non-linear magnetic waves are decoupled. In other words, when we have magnetic energy, we don't have any kinetic energy. That's interesting. That means that non-linear fast and slow waves are decoupled. And finally, we found that alpha wave propagations around the null point results in fast and slow magnetic waves perturbations due to the destruction. Fast and slow waves perturbations aren't significant, and they don't result in high current density accumulation at null point. Then we don't have any magnetic connection in this case. That initial fast magnetic wave results in high current density accumulation at null point, and then it leads to magnetic reconnection and also significant plasma flows. Thanks everyone. If you have any question, please let me know and send your questions by email.